This is a raw silicon processor operating in isolation, no external cooling, no server racks, and no connection to the outside world. It is an ESP32S3 microcontroller, an $8 chip, and it is currently running a language model with 28.9 million parameters. For this specific hardware, the performance is remarkable. It generates coherent text at roughly 9.5 tokens per second. Every step of the inference process is handled locally. The chip is not sending queries to a data center. The entire model lives and breathes inside this single piece of plastic and wire. Achieving this speed on an $8 chip contradicts standard industry expectations for edge AI, where hardware at this tier is usually relegated to simple sensor monitoring. Until recently, running a language model on a chip with these memory specs meant hitting a hard ceiling at about 260,000 parameters. This chart visualizes that gap. The small sliver on the left is the historical maximum of 260,000 parameters. The column on the right is the new baseline, 28.9 million. That represents a 100-fold increase in computational capacity, running on the exact same silicon. This leap was not the result of a hardware upgrade. It was achieved through a strategic architectural exploit in how the model accesses its own data. The fact that this hardware can sustain 9.5 tokens per second suggests that the historical barrier was less about a lack of processing power and more about a rigid approach to parameter allocation. To understand the fix, we have to look at the physical layout of the ESP32S3 chip. The primary constraint of any microcontroller is its memory. These chips are designed for efficiency, leaving very little room for high-speed working memory. Specifically, the ESP32S3 contains only 512 kilobytes of SRAM. Standard AI deployment assumes that every active parameter in a neural network must be stored in that fast SRAM to be reachable during inference. The math of that requirement is impossible for a model this size. You cannot fit 29 million parameters into a 512 kilobyte space. This is the memory wall, the physical bottleneck that usually forces edge devices to offload their thinking to the cloud. Bypassing that wall requires moving away from the idea that the entire model needs to reside in fast memory simultaneously. This architecture splits the workload across 3 memory zones: 512 kilobytes of fast SRAM at the top, 8 megabytes of PSRAM in the middle, and 16 megabytes of slow flash storage at the bottom. The model's foundation, a 25 million row embedding table, is locked entirely into the slow flash tier. This utilizes per-layer embeddings, a technique adapted from Google's Gemma models. In this design, the embedding table is treated as a read-only resource. The model reads from this table rather than performing complex computations against it. For each token generated, the model pulls only the specific rows it needs, about 450 bytes, and routes them from the slow flash up into the fast SRAM core. The 8 megabyte PSRAM layer acts as a buffer, handling the intermediate activations as the model cycles through its layers. This leaves a very small reasoning core in the SRAM to do the actual work. It is the only part of the model that stays permanently in fast memory. By treating the bulk of the model as a passive lookup table, we remove the requirement for massive SRAM capacity. Because the majority of the 29 million parameters are never loaded at once, the computational cost of running a large model becomes negligible. To make this work, the total model footprint still has to stay under the 16 megabyte capacity of the flash storage. Using 4-bit quantization, the 28.9 million parameters are compressed down to 14.9 megabytes. This compression comes with specific trade-offs. While the model is linguistically coherent, it cannot recall facts, write code, or follow complex instructions. These limits are a result of the TinyStories training set, which focuses purely on the structural logic of simple synthetic narratives. It is critically important to distinguish between the model's limited knowledge and the success of its underlying architecture. The reasoning restrictions are tied to the size of the active compute core, but the per-layer embedding strategy itself remains a viable way to deploy specialized logic at the edge. At this scale, we can see the sheer density of information being routed across these microscopic pathways in real time. This project represents a shift in how we approach edge AI, treating the memory wall as a routing puzzle to be solved, rather than a hardware limit we have to accept. Pulling just a few hundred bytes per token from a massive passive store of data is a radical gain in efficiency. It provides a blueprint for running high-parameter tasks on device, bypassing the traditional reliance on cloud-based compute. Hardware cost and onboard SRAM are no longer the absolute barriers they once were. The ESP32S3 is a standard component in the global ecosystem of low-cost embedded hardware. Applying this logic means existing industrial sensors and IoT endpoints could be upgraded with 30 million parameter models without replacing a single circuit board. Imagine this capability multiplied across the millions of identical devices already operating worldwide. What becomes possible when cheap, offline microcontrollers can perform localized language parsing and reasoning? At Synthic Labs, we are moving these capabilities out of research papers and into functional prototypes. This architectural shift creates a completely new path for complex intelligence to operate in any environment, untethered from the cloud.